Boolean logic can quickly become a maze of complex algebraic equations. To simplify these expressions efficiently, we can translate raw data from a truth table directly into a visual grid called a Karnaugh map, or K-map. This chart displays a standard four-variable truth table on the left alongside two possible Karnaugh map layouts on the right. The table processes four binary inputs, A, B, C, and D, to generate a single binary output, labeled F. The 16 possible combinations of these inputs represent rows 0 through 15. We call these rows minterms. A minterm is simply a specific combination of input variables that produces a specific logic state. When reading these inputs to determine our minterm number, we follow a strict significance order, A, B, C, D. Variable A is the most significant bit, determining the highest value, while variable D is the least significant bit. Looking at the two K-maps on the right, you'll see the axes are labeled with a specific sequence, 0, 0, 0, 1, 1, 1, and 1, 0. This is gray code, a sequence where only one bit changes state between adjacent cells. The brackets on the outside of the map indicate the specific regions where a given variable is equal to 1. You can orient your axes differently, placing A and B on the columns or on the rows, but the logical relationship remains identical. A minterm will map to the exact same relative coordinates, guaranteeing the same simplified mathematical expression regardless of which map layout you use. The K-map's vertical rows represent the states of variables A and B. From top to bottom, they follow a gray code sequence, 0, 0, 0, 1, 1, 1, and 1, 0. This ordering forces adjacent ones in the truth table to physically cluster together on the grid. This schematic shifts focus to the horizontal structure. The four vertical columns represent the specific Boolean states for variables C and D, following that exact same gray code sequence from left to right. This grid displays small yellow numbers nestled inside each cell. These are the minterm numbers. Every single cell in the K-map grid corresponds precisely to one minterm row in the truth table. The K-map acts as a direct, one-to-one spatial coordinate system for binary logic states. This graphic demonstrates the translation of minterm 0. In row 0, inputs A, B, C, and D are all 0, resulting in an output of 1. We plot that 1 in the top left cell at coordinate 0, 0, 0, 0. This image tracks the next step. Minterm 1 has inputs of 0, 0, 0, 1, resulting in an output of 0. We map this 0 into the second cell of the top row at coordinate 0, 0, 0, 1. For minterm 2, the inputs 0, 0, 1, 0 output a 1, mapping to the far right column. Notice it skips the third column. Because gray code places 1, 1 before 1, 0, minterm 2 isn't placed sequentially. Counting straight across points in the wrong cells. This completed layout displays the grid after all 16 minterms have been successfully transferred from the truth table. With the raw data fully spatialized, we can now solve complex algebraic factoring through purely visual pattern recognition. This specific K-map highlights a vertical grouping of 4 ones on the right edge. Grouping adjacent ones in powers of 2, like 2, 4, or 8, allows us to apply the uniting theorem. This theorem states that any variable that changes state within a grouped block is mathematically eliminated from the expression. Looking at this vertical group in the 1, 0 column, the column variables C and D remain constant at 1 and 0. However, the row variables A and B change state across the 4 cells. Because A and B change, they are eliminated, and the entire block simplifies to just C and not D. This diagram highlights a 2 by 2 square grouping of ones in the lower left corner. Within this square, variable A is consistently 1, and variable C is consistently 0. Variables B and D change state across the boundaries of the square, so they are eliminated. The group simplifies to A and not C. This layout illustrates a larger group of 8 minterms forming a vertical block. Because the group spans all 4 rows and 2 columns, variables A, B, and D all change state and drop out, leaving only variable C. This graphic presents an alternative 8 minterm scenario with a horizontal block. Here, it spans all 4 columns and 2 rows, eliminating B, C, and D to simplify down to just variable A. The visual rule is consistent. The larger the group of ones you can draw on the board, the more variables drop out, resulting in much simpler logic for the final hardware. Applying these rules to our original dataset, step 1 is finding the largest block. We group these 4 ones in the upper right corner. Variables b and d change state. Eliminating them gives our first simplified term, a0 and c. We have 4 unmapped ones on the bottom row, grouped in one horizontal block. Across this row, variables c and d cycle through states and cancel out, leaving the term a and b0. Every high state is now grouped. By accounting for every one in the fewest, largest groups possible, we guarantee a fully optimized logic design. This graphic shows the final result. By adding our extracted terms together, the simplified Boolean expression for the entire circuit is f equals a and b0, or a0 and c. Look at the text at the bottom. That is the manual Boolean algebra required to factor out the same exact result. It is a long, tedious string of calculations where a single misplaced variable derails the equation. The Karnaugh map replaces that math with geometry. By mapping data points to a precise grid, it turns time-consuming algebraic factoring into a solvable, visual picture puzzle.
Thanks for watching. See you next time.